This is on the one sample t-test. In the example I gave you, I said that a researcher was interested in the mean of a certain population. More specifically, the researcher was interested in the mean age of a certain population. And the researcher can't calculate the population mean because the population is too large, and it's not possible to ask every population member for his or her age. But the researcher can use a sample and record the ages of the sample, and then if the researcher can calculate the mean of the sample, the researcher can use that as a way to make the best possible decision about the population mean. Because since the sample comes from the population, it makes sense that the mean of the sample would be useful to make a decision about the mean of the population. So what the researcher can do is choose a hypothetical number that the unknown population mean might equal, and the researcher can actually choose any number that he or she likes. But there's usually a theoretical reason for picking a certain number. In this case, I decided to work with 24.5 as a possible population mean, but I didn't have to choose 24.5. But let's say that I'm a researcher and I actually did choose this number as the hypothetical value of the population mean. I've decided to test this number as a possible value of the population mean. I take a sample, in this case, of 3 people from the population, and I calculate the mean of the sample. These are some possible outcomes that I might end up getting if I record the ages of all 3 people in the sample, and then I calculate the mean of my 3 people. Well, if I get a sample of 3 people with a sample mean that equals the hypothetical number that I selected, then the t-score will be 0. The t-score is 0 when the mean of your sample equals the hypothetical value that you selected as a possible population mean. If the sample mean comes out higher than your hypothetical value, your t-score will be positive, and the further your sample mean is above your hypothetical value, the further your t-score will be above 0, because we can see that when the sample mean goes from 24.5 up to 26.5, and the sample mean is now 2 higher than the hypothetical value, the t-score goes up to 1.15. And when the sample mean goes up to 28.5, and the sample mean is now 4 higher than the hypothetical value, the t-score goes up to 6.93. So the further the sample mean is above the hypothetical value, the further the t-score will be above 0. We can also see that if the mean of the sample comes out lower than your hypothetical value, the t-score will be negative, and the further the sample mean comes out below your hypothetical value, the further below 0 the t-score will be, because we see here that the sample mean dropped to 2 lower than the hypothetical value. The sample mean is dropping from equaling the hypothetical value to being 2 lower than the hypothetical value, and the t-score is going below 0. And when the sample mean drops to 4 lower than the hypothetical value, the t-score gets even further below 0. So we can see how the sample mean, we can see how the t-score depends on the difference between the sample mean and the hypothetical value that the researcher selected. That's a little bit oversimplified, because we can see that these two samples we can see that these 2 sample means are both 2 lower than 24.5. They're both 22.5, which means they're the same distance below the hypothetical value, but they have different t-scores because of the different standard deviations. But even though that's true, we can still see the general pattern that as the sample mean goes further below the hypothetical value, which is up here, the t-score goes further below 0. As the sample mean gets further above the hypothetical value that's up here, the t-score goes further above 0. Now, let's talk about why this is actually important. We actually care about the mean of the population that this sample came from. And we're considering the possibility that the mean of the population is 24.5. We have a null hypothesis and an alternative hypothesis. The null hypothesis says that the hypothetical value is correct and that the actual population mean does equal 24.5. The alternative is the opposite. The alternative hypothesis says that the hypothetical value is not correct and the mean of the population is not equal to 24.5. I should have had a not equal sign here because the alternative always has not equal in it. The null hypothesis has the equal sign. Now, before we talk about that some more, I wanted to talk about how the sample mean that we end up getting down here is likely to be somewhere close to what the mean, what the actual population mean is, because if we're randomly taking a sample from a population, the sample mean should fall somewhere close to the population mean, meaning in that case, the sample mean should be, when the sample is random, the sample mean is likely to be close to the population mean and is less likely to be further away from the population mean. And I wanted to make a diagram to make that point. Let's say that the actual population mean, which is unknown to the researcher, is this x right here. If the sample was randomly selected, the sample mean is more likely to be close to the population mean and is less likely to be further away from the population mean. So we can imagine that the sample mean is likely to be somewhere within these boundaries, meaning somewhere near the population mean. The sample mean is unlikely to be down here too far below the population mean, and it's unlikely to be up here too far above the population mean. It's likely to be somewhere close inside of here. So let's look at a situation in which the actual population mean, which is the red X, is actually equal to a hypothetical number that I'm working with, at 24.5. What we can do is we can set the red X to 24.5. If the unknown population mean is actually right here at 24.5, the sample mean is likely to be somewhere near 24.5. So I'm just trying to ask you to imagine how if the unknown population mean is right here at 24.5, the sample mean is likely to fall somewhere inside of these boundaries. it won't necessarily be exactly at 24.5, but maybe a little bit above or somewhat a little bit below, but somewhere in a certain range. You can see that this is the situation in which the null hypothesis is true, because the actual population mean is 24.5. The actual population mean is equal to my hypothetical number. And in this case, I'm likely to get a sample mean somewhere near 24.5, because that is the actual population mean. And because of that, I'm likely to get one of these t-scores near 0, because notice how the outcomes with a sample mean near 24.5 produce t-scores near 0. The samples that are near the center give you t-scores near 0. But what if the null hypothesis is not correct? What if the sample mean, what if the actual population mean is down here? What if it's at 22.5? In this case, the alternative is true, because the actual population mean is not at 24.5. In this case, I'm likely to get a sample mean down here close to this population mean. If the population mean has actually been shifted down here, then the sample mean should be somewhere around the actual population mean down here. And in this situation, I'm likely to get a sample mean somewhere around here, around the 22 area. And because of that, I'm likely to get one of these t-scores that are further toward the negative end. And if the unknown population mean is actually above 24.5 up here somewhere, then like up at 26.5, then I'm likely to get a sample mean somewhere around the actual population mean up here. And because of that, I'm likely to get one of these t-scores further above 0, because we can see that the sample means that are up here, up higher above 24.5, produce the t-scores that are further above 0. So overall, we don't know what the actual population mean is. We don't know what where the red X is actually located. If it's located at 24.5, which is the hypothetical population mean, the null is true, because the population mean is 24.5. Then the hypothetical mean and the actual population mean line up in this case. In this situation, the sample mean, the X bar, is likely to be somewhere around the red X, around the actual population mean right here, and you're likely to get one of these t-scores near 0. If the actual population mean is somewhere lower, down here, you're likely to get a sample mean somewhere around that. And because of that, because you're likely to get a sample mean down here somewhere, you're likely to get one of these more highly negative t-scores. If the actual population mean is actually somewhere up higher, above 24.5, we're likely to get a sample mean somewhere higher, because if the actual population mean is higher, then the sample mean is likely to fall in this higher range up here. And because of that, we're likely to get an outcome up here with a more highly positive t-score.